Hello, my name is Christopher One, and I'm a student at Hunter College High School.
And my name is Lily Michal Wilson, and I'm also a student at Hunter College High School.
Our presentation today is going to be on the automated classification of students on Twitter using simple profile information. Social media is often used in research to identify differences in attitudes and behaviors of specific demographic groups within a population. However, many social media platforms do not provide detailed demographic information for researchers to use, necessitating the development of external classification techniques. Automated demographic classification allows us to analyze large groups of social media users in social science research. In the past, researchers have developed age and gender classifiers, or created models to detect organization accounts and spam accounts. The image on the slide illustrates a typical workflow for creating a machine learning classification model on Twitter. We start by manually labeling a user dataset, then feed our training data into a machine learning model. We ultimately get final results based on predictions in the test dataset.
In this project, we looked at classifying students on Twitter. This demographic is important because of the fact that young and educated users are overrepresented on the platform, as shown in the figure on the right. Some applications of a student classifier are 1. Social science research, looking at the impact of an academic environment on online behaviors. 2. Professional networking, for example, helping students locate professional mentors or other students with similar interests. Or 3. Targeted resource allocation, pointing students towards educational or professional resources online. The only previously published reproducible student identification model was proposed in He et al. 2016. This model analyzed the contents of a user's tweets to determine if they were a student or a non-student. Although their model achieved a high accuracy of 84%, its use of tweet content was restrictive because of the nature of the Twitter API, which we'll explain on the next slide.
With this project, we aimed to develop a student classification model that was, first, more generalizable. The model Lily previously mentioned used a semi-automated dataset construction method which relied on identifying regular expressions within a user's tweets, which could have introduced some bias into their dataset, to create a tool which could be more widely applied in social media-based research. We manually labeled our dataset through thorough examinations of a user's entire internet presence. We also wanted the tool to be more accessible. While the aforementioned model used tweet content, we aimed to create a model which would use only profile information to classify students. This approach would allow users to bypass Twitter API restrictions and tweet privacy restrictions when using our model. The third goal was efficiency. A profile-based approach also simplifies the data collection process. Due to rate-limiting features of the Twitter API, collecting profile information is much faster than collecting tweet data, allowing approximately 100 times as many users to be analyzed within a rate limit period of 15 minutes. Our final goal was to maintain the same high accuracy achieved in previous works. We thus utilized 6 different model candidates and picked the best performing choices to investigate further, which we will discuss later on.
The first part of our project was constructing a student-dense dataset to train our model. In order to do this, we scraped users from 3 different sources and manually labeled them. The first source was a general Twitter stream for 10 minutes, looking only at English language tweets. The second source was the followers of Hunter College, a university account on Twitter, which we thought would increase the proportion of students in our set. And finally, we looked at the Who to Follow feature on Twitter, which was used to find the friends of previously identified student users to further increase the number of students in our sample. After gathering a sample of users, we manually labeled them using their Twitter bios, tweets, and associated online profiles. An example of user bios is included in the bottom left. We had defined students as users in high school, undergraduate, or graduate school as of spring 2020, and non-students as users who had already graduated or had a full-time job.
To develop the inputs for our machine learning models, we analyzed the content of user profiles. We developed 10 text-based features, which were features based on the descriptions or names of each user, and 10 metadata features, which were direct data points about the user, such as the number of followers or friends. We ultimately removed three features because they decreased the overall model performance. That can be seen in the table to the right. We then conducted an ablation study to verify the importance of our 17 remaining features, and found that all 17 had a positive relative importance to the model. The results of this study are also in the figure to the left.
After collecting data and choosing features, we set up 6 different models to run student classification: logistic regression, random forest, k-nearest neighbors, a support vector machine, AdaBoost, and the stacked classifier. The stacked classifier is pictured to the side because it uses the outputs of the previous models as inputs to a logistic regression model. In order to provide points for comparison, we created 2 baseline models. On the previous slide, in the ablation study, we found that one feature had extremely high importance. In order to see if the other 16 features contributed to more accurate classifications, we used an if statement model, which predicts users as a student or non-student solely based on that one extremely important feature. We also reproduced the tweet content-based model described earlier using our own dataset.
After training, optimizing, and testing each model, we extracted 3 metrics: accuracy, F1 score, and the AUROC curve, or the area under the receiver operating characteristic curve. Based on these results, we found that the top 3 models were the logistic regression, random forest, and stacked classifier models, due to the relatively high statistics in each category. In addition, based on the results from our 2 baseline models, we were able to conclude that our dataset labeling methods and hyperspecific profile-based features also contributed to an increased success in student classifications.
In conclusion, we demonstrate that it is possible to increase accessibility, efficiency, and accuracy through a profile-based approach to student identification. The success of our profile-based models suggests that it may be valuable to consider how to improve them further. First, due to our time-intensive manual labeling process, we trained our model on a relatively small 1,000 user set. Using a larger dataset could yield improved results. In addition, we noticed that there were several organizations catered towards students among our incorrectly classified users. Pairing our tool with other classifiers, such as an organization classifier, could increase the success of our model in future practical applications.
Thank you for listening to our talk on profile-based student identification on Twitter. If you are interested in hearing more, please contact us at the contact information listed on this slide.